First, I want to thank Yugabyte for putting on DSS and providing a forum for thought leadership around distributed SQL. So I'm pretty excited about today and the sessions that are come. Today, I'm going to spend some time and take the opportunity to share our journey building a next generation cybersecurity service that led us down the path to distributed SQL. Before I do that, I'm going to jump in, introduce myself a little bit, and then we'll get into it. So I'm Jake Roersma, as Karthik said. I'm the SVP of Platform Engineering at Netskope. Over the last 6 years, I've been leading the development of our cloud infrastructure platform that underpins all of Netskope's services. My career has spanned about 2.5 decades, primarily working for global internet companies where I've been building in leading teams that have been building distributed services at scale with global internet reach. As I mentioned, I'm pretty excited to share our story. This is about our next generation CASB API service in our path to distributed SQL. There'll be three key takeaways that I'd like you to walk away with from today. First is just a high-level understanding of Netskope and our services and why they matter. Second is sharing our experience building high-scale cloud-native solutions. And then finally, how we solved our data reliability, scalability, and performance needs with distributed SQL systems. So who is Netskope? Netskope is a cybersecurity company founded in 2012. We are a leader in the security service edge market sector. And as you can see, we're in the upper right corner of the Gartner quadrant. Security service edge, I'll get into that on the next slide and try to simplify that for you. But it's, we're also in this space that brings the WAN edge with security edge together, also referred to as SASE. So I'll get into that here in a second. SSE and SASE explained, as I mentioned, SSE is really the combination of critical security services delivered at the edge, nearest the end user and the SaaS providers. The WAN edge brings the WAN services such as SD-WAN and couples that with the security services that provides an on-ramp to the internet that's secure, fast, and reliable. At Netskope, we call this platform the Netskope One platform. I could speak at length about the digital transformation over the last 20 years, but I think we all know that's really accelerated in the last decade or so. Over that time, enterprises flocked to SaaS services, moving out of their data centers, which pushed the security services and the need for security services out to the edge. And then, as we know, in the last 4 or 5 years, hybrid and remote work has become more and more commonplace, which further extends the edge in which we need to secure. And as a result, data is everywhere. The most important data that needs to be protected is on end user devices, whether those are phones, laptops, IoT devices. It literally is everywhere. So what this did, this digital transformation and expansion of the security edge is it resulted in disparate, isolated, independent security services to solve for data loss prevention, secure web gateway, cloud access security brokers, and so on and so forth. And so the user, fundamentally this created two problems. One is it made it very difficult to secure because you have these isolated solutions that are independently configured, independently managed, and then the user experience was poor because some of these services need to be chained, some of these services are deployed at the edge, and some of them weren't. What SASE does is it collapses all of these critical security functions into a secure edge and allows all of these security applications to run on the edge most closest to the users and the SaaS providers that provides a fast, reliable user experience without compromising security. So none of this would be possible without a private cloud infrastructure that can actually run on the edge and run all of these security services. So Netskope has, our platform engineering team has built out what we call the new edge, which is a private cloud compute, is the largest SASE and most connected SASE edge on the planet. We're deployed in 80 regions, which makes us fast and reliable. And then that's supported by 12 management plane regions where we do our central data processing. So the 12 regions I'll talk about at length today, because that's what supports the portion of CASB that I'm going to speak to that led us to distributed SQL. So a little bit more on CASB, and then we'll get into the database details and the journey. So CASB is a cloud access security broker. So as enterprises adopted SaaS, the need for security between the user and the SaaS providers arose. And so the reason this exists is for a couple of reasons. One is to govern usage. So not all SaaS applications are safe. Not all are approved by the enterprise, and so on and so forth. So the CASB allows us to govern which SaaS providers are allowed and how they're used. Second, there's a lot of data in these SaaS providers. That's corporate data, intellectual property. It needs to be secured. It needs to be classified, and you need to be able to enforce policy on that data. And then lastly, you have to protect against threats, whether those are internal threats, malware, data sharing, so on and so forth. And the CASB allows you to do this. The Netskope CASB platform supports over 400 SaaS providers and provides security, real-time security for tens of millions of users in the corporate space. There's two flavors of CASB that I'll talk about. One is CASB inline, and that sits between the end users and the SaaS providers in real time, applying security to API calls as they flow through the network. And then the second is CASB API, which is an out-of-band SaaS integration that works with the cloud providers' APIs or SaaS providers' APIs to provide out-of-band security functions for changes that might not happen in those real-time scenarios. So I spoke a little bit about CASB API, and CASB API was something developed at Netskope early on in our journey. And as we went through our journey, a couple of key challenges that we saw in the marketplace. One was the number of SaaS providers was growing significantly, especially SaaS providers that were important to enterprises. So the velocity of keeping up with these SaaS providers became paramount, and having a framework that we could develop those quickly with cloud native applications was critical. Another key point here is we needed to scale with the SaaS providers. A lot of these SaaS providers are deployed in public cloud. Some of them are the public cloud. So these SaaS providers can, in some cases, infinitely scale, and it's important that we are able to scale with them. And one key aspect of cloud native, in addition to the few that Karthik mentioned, is protecting the cloud services. So one thing we often run into, especially with integrating with SaaS provider APIs, is being rate limited. So we have to provide a high performance product, in the face of being rate limited on a per customer, per app instance basis. And so we want to sort of ride that line right at the rate limit, where it doesn't affect our service and our capability. So why the change? Why did we have to do this, cloud native next gen CASB API? And I mentioned some of the market opportunities, the need for higher velocity to keep up with the SaaS frameworks. Cloud native was a must. We needed to be able to scale up and down. We needed the resiliency that comes with cloud native applications, assuming infrastructure failure, being able to work around it, all while providing high performance. So some of the data specific challenges, which I'll kind of go through in another slide as we get further on here, is we originally chose MongoDB as sort of a universal data store early on in our startup journey. This provided easy access. We made it very simple for developers to integrate with MongoDB. But as you can imagine, as we scaled, it presented workload challenges where potentially the wrong types of data were in MongoDB, or we had conflicting workloads as we scaled. Eventually, what that resulted in at scale is sort of conflict of workloads. Our OLTP and OLAP workloads were co-located. This became a problem at scale years into our development, and I'll kind of go through those details in a little bit. So we still run MongoDB today. It is a part of our legacy workload. It's a fairly significant deployment, somewhere around 100,000 cores globally. And some of our larger clusters have 300,000 or more collections, which if you work with MongoDB, that can be very problematic at that scale. So why Yugabyte? Yugabyte for a couple of reasons, and I'll walk through kind of these requirements quickly. That when we assess the distributed SQL environment, say in 2020, 2021, we looked at a number of data technologies, and what led us to Yugabyte was the ease of use, reliability, and scalability of the platform. As I mentioned, and I'll get to the reason why. Actually, I'll start with the reason why. Scaling up and scaling down is just important to us, and that's a key aspect of a cloud-native application. One of the challenges that we have with the CASB API is we're brokering API calls for tens of millions of users, hundreds of SaaS applications that are on individual instances. And as I mentioned, the CASB API is designed to handle the out-of-band transactions that happen in these SaaS providers. So oftentimes those out-of-band transactions are happening due to integrations between SaaS providers. So a single transaction in a SaaS provider might amplify into thousands or tens of thousands of webhooks that come from the SaaS providers that we need to process and apply security to. So the scale is pretty significant. The other aspect that requires us to scale up and potentially then scale down is onboarding existing SaaS applications. So you take a large enterprise with hundreds of thousands of users using a SaaS app with billions of objects or billions of files. So in that case, we need to onboard that SaaS provider and apply security policy to the existing workload. And so you potentially have hundreds of billions of permutations of users, applications, and security objects that security policy needs to be applied to. And we need to be able to scale up to process that quickly. And from that point, manage the steady state. So in some cases, this scale can be 10 to 20x requirement to onboard large customers. The ease of use and the scale up, scale down I covered. We're also interested in some of the other feature sets such as row level security and change data capture, which I'll get into. And then lastly, we knew that we wanted ACID transactions eventually, which I'll walk through that in a minute here. So this is our journey. As I mentioned, we started with Mongo at the beginning of our startup journey. In about 2017, we realized that we needed the next gen CASB for the reasons I had mentioned. We started development. We prototyped that with SQLite running in the pods that are tenant app instance specific in Kubernetes. And then we piloted initially a distributed data system with Scylla. And what we came to find out when we were running Scylla at scale for this workload is that consistency actually was going to matter for us. And so the eventuality of needing some of those ACID transaction capabilities kind of came to the forefront, and we realized that we needed to transition. One of the trade-offs we made with Scylla and accepted, in addition to the ACID transaction, was moving away from our desire to use SQL. We wanted to use SQL for a lot of reasons, but we felt that was a reasonable trade-off to get a distributed system at scale on the data side. And that in itself also proved problematic. Not every developer is adept in NoSQL semantics. and schemas. And so it made that definitely challenging, and our data model was highly relational. So we moved forward and we reevaluated. We ended up selecting Yugabyte for all the reasons I mentioned on the other slide related to availability, reliability, and scalability, in addition to the feature sets that we needed to sort of separate our workloads, including CDC. So we're kind of midway in our journey here. In 2022, we started to pilot customers on the new CASB Next Gen. 2023, all of our new apps were built and deployed on the CASB Next Gen, and we're about 30% away through our migration of the legacy workloads onto the new CASB Next Gen. So this is just a view of our data flow. The CASB apps, as I mentioned, run in Kubernetes. They're isolated by a tenant app instance. They individually scale and provide that capability. They're integrated with Yugabyte through a service that we built called DBaaS that helps facilitate the application lifecycle with the database lifecycle and integrates with Yugabyte APIs. And then, as I mentioned, we're early adopter for CDC. And I'll kind of go through some of the technical details of that in a future slide. But what CDC allows us to do is separate the OLTP workload from the OLAP workload. And so this is something that we partnered early on with Yugabyte. We implemented, help test, and pilot in our environment. And it's something definitely that works at scale for us. To separate those workloads, and that data streams through Kafka, and then gets written to ClickHouse DB, which is used for the analytics and reporting in our web UI. So more on our experience running Yugabyte. First, as I mentioned, Netskope is deployed in 80 regions with 12 data processing regions that support our real-time, SASE products. 100% of the processing we're talking about here today is on-prem in our private cloud, and the Yugabyte deployment, which I'll go into on the next slide, really fit well into our resiliency story, into our deployment model, and so on. So what we found is Yugabyte has been extremely reliable. I'll talk about this in a couple of slides, but the ability to manage the lifecycle, as Karthik mentioned, upgrades, outages, gray outages, it's been extremely reliable and provides us 5 nines of uptime. Next, excellent performance, and it scales well up and down. So we've scaled out Yugabyte. We've vertically scaled Yugabyte. We ended up kind of finding a sweet spot for our workloads in terms of the vertical scale, and then we're able to scale it down in the cases that we need it to. As I mentioned, we're using change data capture. I'll go through some of the technical details of that in a second, and then the open source and commercial support from Yugabyte has been phenomenal. So a little bit on reliability. This is kind of a busy slide, but the main point here is, any modern cloud infrastructure is going to be based on a deployment architecture that's layers of isolation and resilience. And the layers are important, and Yugabyte, being a distributed database, allowed us to map the distributed database to our physical layers and compute. So what this has allowed is not just at the Yugabyte layer to be able to manage the resilience and lifecycle, but it's also allowed us to manage the underlying infrastructure without disrupting the database. Our deployment, probably just talk a little more on the layers of isolation. So we have multiple management planes in 12 regions, like I mentioned. And our tenants are assigned to one of those based on their needs or data jurisdiction. And in those management planes, we have multiple Yugabyte cluster or Yugabyte DB clusters where we shard the tenants across those for isolation purposes. And then in addition to that, the Yugabyte DB nodes are spread across our AZs to provide resiliency to failure. As I mentioned, this deployment has been out there, I think, for around 3 years, and has been running at 5.9. So it's been super highly resilient at scale, and that's been pretty important to us. So talk about our scale, kind of get to the brass tacks and talk about what we're experiencing. So our current deployment is 42 clusters across the 12 regions that I had mentioned. Each region has multiple clusters, and as I mentioned, we shard our tenants across those. Today, we're nearing a petabyte replicated worth of data across these clusters. So we're at 822 terabytes globally. And one key aspect that I didn't mention that's super important is compression. So the 822 uncompressed ends up being 176 compressed. So that's a pretty impressive stat. And then lastly, in those 42 clusters, we're just shy of 8,000 cores that supports it. As we work through our migration, as I mentioned, the onboarding in our CASB API can be extremely CPU intense, and the scale up not only of the compute in Kubernetes, but the scale up of Yugabyte has been will allow us to scale that 8,000 cores into 15 or 20,000 to support the onboarding or migration of the CASB API instances that we have for our customers. And then, as I mentioned, scale down is very important. That onboarding process can be single-digit days, and we may need to scale down, or we will scale down after that. All right, here's a snapshot from the application side. So this is a single cluster in one of our management planes, or I guess the apps that are supported by a single Yugabyte cluster in one of our management planes. And you can see these are application processing throughput in a single day for some of our larger SaaS apps that CASB API supports. And I think point out that OneDrive on this is, in a single day, we're doing 2.2 billion transactions in 24 hours. And how that translates to the workload on the Yugabyte DB side is about 4 to 8x. So each application transaction, as we're tracking the state, as we're processing and applying security policy, ends up being 4 to 8 times more transactions on the database side. So that 2.2 billion alone ends up being 8 to 16 billion on the Yugabyte side, reads and writes. So getting into the Yugabyte performance and scale, here's some numbers from that same cluster in our largest site. And as you can see, probably the biggest sort of thing to highlight on this is our write workloads are, the mean of that is about 11,500 operations per second. And what's important here, I guess we're not seeing it, but is with writes and distributed data systems, the thing you worry about is the latency, right? So you have multiple nodes that need to take the write before they're considered committed and the application can move on. So the difference between the mean 2.7 milliseconds for writes and the P95th is 3.9 milliseconds. So you got about 1.3 milliseconds different, 1.2 milliseconds different between the mean and the P95th. So a really, really low variance in a distributed SQL system in our environment at scale. So it's really, really impressive. It's probably worth pointing out that this scales horizontally, right? So as we add more T servers, these metrics stay pretty much the same. And so we've, at first when we adopted Yugabyte, we thought we would limit the number of T servers to 5 per cluster, and then we would scale out the clusters. And I think that's sort of a little bit driven by sort of non-distributed SQL systems or NoSQL systems where we assumed that the horizontal scale needed to be limited long-term. And so what we found out is that's not true. We've scaled up the T servers significantly in some cases, and then we've scaled them down, all while maintaining that right performance for our workloads. The read performance maybe a little bit easier in the distributed SQL world, or I guess less complex. As Karthik pointed out, the thing to worry about here is sort of those those gray failures, right? The performance degradations due to failing infrastructure, and so our private cloud is built on commodity hardware. We have failures just like the public cloud has failures. We have drives that slow down. We have drives that mysteriously have errors, and and so like we're no stranger to the sort of gray failures, and Yugabytes work really well in those scenarios. This graph is showing that we're doing about 47,000 reads per second on average, and the reads are sub milliseconds. So we're in the half a millisecond range with really again low variance between the mean and the p95th. So change data capture, as I mentioned, one of the drawbacks from, or I guess one of the positive sides of MongoDB is that you can run OLAP and OLTP workloads on the same cluster. And what we found out is it doesn't work well at scale. It doesn't work well when you commingle the schemas. And so what we wanted to do is get away from that. And so CDC really has enabled us to move data between data systems to optimize for those workloads. And so, as I mentioned, we were early adopter with Yugabyte on their implementation of CDC. We piloted it, we tested it, and it's been GA for some time now. And that allows us to move data from Yugabyte DB through Kafka to ClickHouse DB for the OLAP workload. What these graphs are showing here is that and I think the graphs that show before is we're operating at scales, tens of thousands of transactions a second on the right side, and that throughput goes through CDC, goes through Kafka and ClickHouse, and on average we're low double-digit milliseconds latency out of Yugabyte. So it's really impressive how it keeps up. So looking forward, there's more for us to do on our Yugabyte journey. First is to finish our migration. So we're going to scale up. We're going to migrate our users on CASB API from the legacy to the next gen system that's backed by Yugabyte DB. And then we'll scale down the Yugabyte and compute side of that to manage the steady state of those applications. So looking a little bit further out past the migration, we'd like to get back to row level security. We started there. We piloted row level security. We had some performance challenges with that, and that definitely needed some more work in terms of how we implemented and how the schemas were made. I think Karthik mentioned this. The Postgres native workloads are very interesting to us. So early on in our distributed SQL journey, what we found is there was a barrier to adoption, and that barrier was having to adjust your schemas to optimize for a distributed SQL system. And for our CASB API, the workloads, we did optimize those for the distributed SQL. It did take some amount of work, but for some of our other workloads that may be ORM based or have sort of complexity deep in the application, adjusting those schemas isn't always possible. And a lot of those schemas don't have to function at scale, but still need the reliability that a distributed SQL will provide. So definitely interested in looking at that. As I mentioned, we deploy Yugabyte on our private cloud. Today we deploy those in VMs. And so all of our compute workload for CASB API runs in Kubernetes. It scales up, it scales down. And so we're going to explore running Yugabyte DB on Kubernetes with those workloads and some of our other workloads. And it's something that will evolve over time. As I mentioned, we built a service that lives sort of adjacent to our compute workloads for CASB API and Yugabyte. And we call this service DBaaS. So this service provides an abstraction as a service layer for common lifecycle operations between the application and Yugabyte, and that integrates with Yugabyte's API. So we'll look to enhance this as the Yugabyte APIs are enhanced, and provide easier self-service for our service teams. All right. Looking into the future in terms of the hyperscale landscape as it relates to distributed SQL. So the first thing I'd like to kind of point out is the infrastructure trends are sort of come and go. Definitely cloud's here to stay, but there was a rush to private cloud tens of years ago. There was a rush to public cloud shortly after. And now what we're finding more and more often is that a multi-cloud strategy is important to resiliency, is important to managing costs, and it's important to provide a reliable service to our customers. And so I think this will become more and more important over time to have a multi-cloud strategy, but more importantly, to make sure that you have the portability to move between clouds or run in multiple clouds. So portability is very important, and I think especially for data systems, the data that we have is growing larger and larger and larger, and being stuck in a non-portable system is definitely not where you want to be. I want to reemphasize the importance of open source. It's not something we talk about often. Obviously, KubeCon and DSS are founded on key technologies that are open source. So it's probably one of the most important things, I think, in terms of evolving hyperscale securely, is having having the core software be open source, having communities like this contribute to it and evolve it. So I think that's key to the hyperscale landscape going forward. I talked a little bit about lowering barriers. I'll just reemphasize that. Barriers adoption, especially at hyperscale. As we hyperscale, data sets become more complex. The infrastructure becomes more complex. So lowering the barriers to entry to that through automation, and other, and I'll get into AI at the end, but lowering the barriers to adopting hyperscale and managing it are going to be super important. I think what Yugabyte and Yugabyte DB are doing in terms of facilitating and lowering the barriers to bring workloads onto Yugabyte are very critical, and kind of make it easier. The problem that where sort of 99% of the data is data at scale and 1% of the use cases, or I think Karthik used 98 and 2% or something like that. But that's what we see is there's the scale data, few of the use cases, and then most of or the lesser the data, 1% of the data is a huge portion of the use cases. So marrying those two is super important for performance and resiliency. So the distributed SQL systems aren't always about scale. The performance and resiliency is a key aspect of it as well. So on security, the security systems and the space that my company operates in has been largely focused on unstructured data in SaaS providers, and so that's typically where you see data infiltration, accidental sharing, malware, those types of things. But the reality is, as data is growing 20, 30, 40% a year, and accelerating with AI and other things, our end users are gaining more and more access through data systems, or to our data systems that have the majority of data that needs to be secured. So structured data is super important, and in the security space, securing that, what we call, is referred to as data security posture management. So I think as we hyperscale and more of that data is in structured data systems, with more and more of our users having access to it, it will be super important. where data systems are going to need to provide the interfaces for security systems to assess the posture management, enforce the posture management. So it is a very critical space, I think, as we hyperscale data. And no tech talk would go undone at this day and age without talking about AI. I'll try to keep this one simple in terms of hyperscaling distributed databases. As I mentioned, hyperscale is introducing more and more data and more complex data systems and infrastructure systems that support it. And so I think from my perspective, as we hyperscale, the AI benefit that we can take away or that can help with hyperscaling is making it easier to manage distributed databases. So in my mind, what this means is leveraging AI to improve query optimization, to create predictive query optimizations. Where we see AI in hyperscale in our business really taking off is helping with anomaly detection, right? And I think as data engineers here, you're no stranger to how complex it is to assess data system performance issues, and I think AI can help with that. If you're looking at across thousands of clusters, millions of metrics, how do you pinpoint those performance issues? How do you make the database tuning and optimizations to help that? So anomaly detection, I think it will be very important as these systems become more complex. And related to that, I think is creating a cycle of adaptive learning that are integrated with these complex systems. To learn and learn how the data is being used, who's using it. I think this kind of overlays with the security aspect as well, is understanding how the data is used and what the data is, who is using it, and how those queries relate to it. So I think that's my view of the AI and hyperscale and how it could simplify that. So I'll end the presentation again with a thank you to Yugabyte for having me, allowing me to share our story. A thank you to our data production engineering team at Netskope and our product engineering teams that helped all this become a reality. And if you have detailed questions, Andrew Bourne's here, who's our architect. He has the answers to all the details, as I'm just a high-level guy. So appreciate it. Thank you, guys.